Here is the first example based on the mutual inductance. So here we see two loops. Okay, there are two inductors and there is a mutual inductance of J2 ohms. Okay, this circuit is already in frequency domain, so we don't need to convert the domain for this. So if it's in time domain, everything, this is going to be in henries, this is going to be ohms, probably this is going to be in sine omega t or cos omega t, something like that. But here it is already in frequency domain, so we can proceed now. So loop 1, I'm assuming I1 current is passing through this. Loop 2, I2 current is passing through this. I'm going to do the loop analysis. So loop 1, apply KVL, Kirchhoff's voltage law. So according to KVL, I'm going to start from the source. Okay, since I'm entering the negative terminal, take that as a negative voltage. If you're entering positive terminal, take that as a positive voltage. So I'm going to assign the positive and negative signs according to my path. So my I1 path is like this. Remember, inductor never produces energy. It's a passive element. It always consumes energy. Okay, so this is plus and minus. Now, so loop 1, apply KVL, it's going to be minus 12. So if I'm entering the negative terminal, take that as a negative voltage, or you can take that as a voltage drop. So negative 12 plus minus J4 times I1 plus J5 times I1. So far, this is what we learned from circuit 1. Okay, so there we don't have mutual inductance, so this would be equal to 0. Now there is a mutual inductance here, so it will come into the picture here. So because of current flowing in this coil, because of the current flowing in coil 2, there is an induced EMF across coil 1. Okay, so what is that? We'll see that. Okay, so we already have self voltage. Let me take that as a voltage V1. This V1 equal to J5I1. Okay, now here is the dot, here is the dot. I want to find, because of this I2, how much voltage is appearing across this coil. I'm going to label that as E1. Okay, E1 equal to M times di2 by dt. That's in time domain. When it comes to the frequency domain, M is nothing but J2 times I2. Okay, now that E1, which terminal is positive, which one terminal is negative? So here this E1 depending upon I2, so find out whether that I2 is entering the dot or leaving the dot. So here current I2 is leaving the dot. That indicates that the dot is at the end of the inductor. Current is entering from here, so dot is at the other end of the inductor, so current is leaving the dot. That's what I meant. So current is leaving the dot, so the dotted terminal must be negative. Okay, so my E1 is going to be J2 times I2. Now is it going to be positive here or minus here? So if you look at that way, my E1 is going to be, this is negative and positive. So everything here, I'm entering the positive terminal, so that's the reason I took this as positive. Entering the positive terminal, took that as a positive. For E1, I'm entering the negative terminal, so I have to take that as a negative. Or another way of saying this is, your V1 and E1, they are in the opposite side, so that's the reason one is positive, another one is negative. So this is our loop 1 equation. Okay, we're going to solve many examples. If you do not understand in the first video itself, don't worry too much. Please watch more and more of my videos, or the future videos, at least 2-3 videos, to understand this dot convention a little bit better. Okay, so this is our first equation. So if I simplify this, I will end up with minus J4I1 plus J5I1, which is J1I1 minus J2I2 equal to 12 at an angle of 0. This is my first equation after simplifying it. Okay, now loop 2, apply KVL. Loop 2, apply KVL, Kirchhoff's voltage law. So according to loop 2, let me redraw the loop 2 here. Okay, I'm assuming I2 current is flowing in this direction. So here is a dot. So J6 and 12 ohm. So according to my I2 direction, so this is plus and minus, this is plus and minus. Okay, let me take this as V2. So here loop 2, so according to my I2 direction, I give positive negative sign, positive negative sign. So 12 I2, I'm assuming I'm starting from there, walking in the anti-clockwise direction. So this is my I2. So 12 clockwise direction, 12 I2, okay, plus J6 I2. So with this we're done with regular KVL equation, but there is a mutual inductance here. So if you look at coil 1, all we care for current flowing in coil 1 and the dots. Okay, so current flowing in coil 1 is entering the dot because the dot is at the entrance of the inductor. So that's what I meant. Current is entering the dot, so the dotted terminal must be plus. So the induced voltage here, E2 will have positive terminal there and negative terminals here. So when I'm walking, I'm entering the negative terminal, so this is negative E2 equal to 0. What is E2? E2 equal to the mutual inductance here, which is J2 I1. Okay, so E2 equal to J2 I1. So 12 I2 plus J6 I2 minus J2 I1 equal to 0. So when I simplify this, minus J2 I1 plus 12 plus J6 I2 equal to 0. Now I'm going to simplify this by multiplying. So this is my second equation, by the way. That's my second equation. So I have two equations, two unknowns. Our goal is finding I2. So what I'm going to do, I'm going to multiply this with the two equation 1, multiply equation 1 with number 2. Okay, numerator. So it's going to be J2 I1 minus J4 I2 equal to 24 at an angle of 0. Second equation, I have minus J2 I1 plus 12 plus J6 I2 equal to 0. Okay, now I'm going to add these two to eliminate I1. So I'll end up with 12 plus J2 I2 equal to 24 at an angle of 0. So our I2 must be equal to 24 at an angle of 0 divided by 12 plus J2. That value equal to, okay, so when I convert this 12 plus J2 into polar format, which is 12.16 at an angle of 9.46, so 24 divided by 12.16, which is 1.97 at an angle of minus 9.46. When I convert that into rectangular format, I2 equal to 0.986 minus J 0.639 ampere. So this is our I2. You can leave your I2 in the polar format or rectangular format, it doesn't matter for me. You can represent your I2 either way. So the two important points we learn, make sure that you include the mutual inductance in both the equations. Okay, I will solve more examples in the next video. Thank you.